Hello. Today's topic is going to be overflow error.
Now there's a couple of things to note about 2's complement that we do need to discuss a little bit, and the first is that so far in all my examples I've been dealing with 8-bit 2's complement, but there's no actual requirement that says it has to be 8-bit. More commonly in a computer system it'll be 16-bit or 32-bit, but in an exam there's no need to stick to that. You might get asked a question about 6-bit 2's complement or a 10-bit 2's complement, and it's important to note that in every single case it's just the most significant bit becomes the sign bit. So right now I'm going to do an example of 6-bit 2's complement. We're going to talk about what would the number 3 base 10 look like in 6-bit 2's complement. Well, first of all, it's important to note that 3 is a positive number, so it's a 2 and a 1, and then we just need to fill out some zeros to make it 6-bit 2's complement. What would -9 look like? Well, let's think over here in our rough workspace. Let's think that 9 is equal to an 8, no 4s, no 2s, no 1s, and then of course we need to make that 6-bit to start with before we then make it negative, which means I'm going to be applying 2's complement to this. In the process of doing this, I start on the right hand side. I start with the right hand side and make sure all zeros stay as zeros until I get to my first one. However, in this case there are no zeros, so my first one stays as a 1, then everything else flips and I get that as my 6-bit 2's complement. You might also get asked questions like what's the maximum value for 6-bit. It should be obvious that in our 6-bit 2's complement, our first bit, this one here, is our sign bit, and so we've actually got units, 2s, 4s, 8s, 16s, and the maximum that we can go to is 1 less than whatever that one bit is. The way that I like to think about it is I think, well, if it was not 2's complement, then that would be the biggest value, which would be our units, 2s, 4s, 8s, 16, 32. That number there represents 32, and thus the maximum that we can represent is actually 1 less than that. So in this case our maximum number is 31. What's our minimum number? Well, it's always the negative of their maximum and then subtract 1. So we can always go further in the negative direction than we can in the positive direction. So 6-bit 2's complement can represent numbers from -32 up to 31. Let's have a look at doing some addition in this 6-bit 2's complement. Right now I'm going to talk about a reasonably tricky addition that we're going to come across, and I'm going to demonstrate how we might do 24 plus 10 in 6-bit 2's complement addition. Let's have a look. 24 we know is going to be a 16 and an 8 and nothing else, but we make it 6-bit, and 10 is going to be an 8 and a 2 and nothing else. Now I'm going to add these two numbers together and see what I get. I'm going to get 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1, 0, put down the 0, carry the 1, 1 plus 1 is 1, 0, put down the 0, carry the 1, 1 gives me that. Now, this is a bit of a problem because if I look at this number, since all my inputs, this one and this one, were positive numbers, 6-bit, then this output here is also going to be, or should be, a positive number in 6-bit. But if we look at this as a 2's complement, then our leading bit here, which is our sign bit, is a 1. And that tells us that it's going to be a negative number. So what actual output this is, let's work it out. If it's negative, we're going to turn this into 2's complement. I'm going to start with make every 0 the same up until my first 1, keep my 1 the same, then flip every other bit. That's what I get. It's the negative version of this number here, which is a 2, a 4 makes 6, plus 8 makes 14, plus 16 makes 30. And I get an answer of negative 30. That seems a little bit strange. How on earth can 24 plus 10 a positive number plus a positive number equal negative 30. Obviously an error has occurred here, and we give that error a name. This is called overflow error. And what's actually happening is that, remember earlier when I said the biggest number we could store in a 6-bit 2's complement was 31? Well, 24 plus 10 we know is 34, which is bigger than the number that we can store. It's literally called overflow because we're trying to put something into a space that can't hold it. And so we're trying to put numbers into these first 5 bits in a 6-bit 2's complement system. Only 5 of the bits are magnitude bits, and the 6th one is our sign bit. And so we're trying to hold magnitude in our magnitude bits that can't be stored in 5 bits. And so it overflows into the 6th bit. This problem doesn't just occur with 6-bit binary, it would also occur in 8-bit binary if we tried to add 2 numbers together that gave a result of more than 127. Or in 16-bit or in 32-bit, as long as we were trying to add 2 numbers together that went over the maximum, we would get an overflow error. Now, an overflow error is particularly interesting because it's not automatically detected by a lot of computer systems. That means that if you ask a reasonably simple computer that is only doing 6-bit calculations, if you ask that to do 24 plus 10, it will tell you that the answer is negative 30, and it won't bat a figurative eyelid. It won't say there's an error here, or it won't register, or it won't warn you that there's an overflow error has occurred. It will just do the overflow error and output the value that it gets. That's one of the reasons why programmers need to be aware of it. It's one of the reasons that it's mentioned in this course as a specific thing you students need to be aware of. Overflow error can occur if you're trying to add 2 numbers in a 2's complement system that don't actually, not even in a 2's complement system. We would also get an error if we were trying to add numbers and they were both unsigned integers, if they would go over the maximum capacity. It won't necessarily tell you that there's been a problem. And so if even in more complex systems, like if we were doing this on a modern computer and we were doing overflow with a 32-bit or a 64-bit integer, we'd still often get the problem just occurring without the computer actually flagging that an error has occurred. So you need to be aware this is a really important error. It is called overflow. A test or an exam situation might mention that specifically. What is the name of the error that has happened here? What are the consequences? You need to be aware of that. So there's another example of overflow that's described on the textbook on page 18. You can read through that and it will talk about some of the consequences as well. That there finishes most of our knowledge on 2's complement that you need to be aware of. There's a bunch of different things you need to know about 2's complement, like how to get numbers into it, how to get numbers out of it, how to read it, how to add numbers with 2's complement, and also some of the consequences like overflow. So now if you have a go at some of the questions for understanding and some of the other things that are given on page 18 should make it very clear. And next lesson we're going to be going on and having a look at some more interesting, some different things that are not related to 2's complement at all, but do require some understanding of 2's complement. All right, I'll leave it there. You do some questions. Thank you.